Okay guys, of course the key has been posted and the video key is there. Any questions before we get going about anything? No lab next week, is that right?
Yes.
We're here Monday and Wednesday, but not Thursday and Friday, is that right?
Yes.
Okay. 2 weeks from today, that Friday, I'll hold a review session. We did one before. What time did we do before? 7 or 7:30? 7:30. 7:30? Okay, that Friday, 7:30, 2 weeks from today. And the test is after that Friday. Okay, stereochemistry. Any questions before we get going? Okay, we're looking at this compound here. I drew on the board. We're D. It's got 2 chiral carbons. We got it here anyway. One thing I want to say about this, guys, hopefully everybody can see this here, is when you're drawing groups on here, you can't just draw groups like this. Okay? This looks like the carbon's bonded to the H and the oxygen is just sort of just hanging out there. That's just not sufficient. You need to have a little more attention to detail than that. Okay? The oxygen is here, then you can put the H there. All right? So we got this compound. 2 chiral carbons, 2 stereogenic sites. 2 to the 2 is 4. 4 stereoisomers max. There could be less sometimes than max. We will see an example of that. Okay, let's draw all 4. Do you have all 4 drawn? I'm going to draw these sort of 4 across, leaving room underneath. Okay? We'll eventually pull this up. Let's see if we can draw these. Because that's generic. That's tetrahedral, but it's not shown. The backbone we're going to keep the same across the board. Okay, we can make the OH bolded. All right, 2 in the plane, 1 forward, H back. And we can make the chlorine bolded. That would be 1. We will get something to write with here. And I should have made that higher. I'm going to go higher here. Backbone the same. We can make the OH bolded, and we can make the chlorine dashed. We can, we can make the OH dashed and make the chlorine, I reckon still dashed. We haven't done that one yet. What else can we do? We can make the OH bolded. No, we've already did that twice. We made the OH dash. And we can make the chlorine bolded. Okay, basically the 2 to the n formula tells us how many perturbations we can be able to do here. All right. 4. And if we had 3 chiral carbons, we'd be able to do 8, because 2 to 3 is 8. Question is, are all 4 of these different? In some cases they may be, and if you have your 4, your maximum number. But if some of them are the same, then it's less than 4. We're just redrawing the same compound a different way. Okay, before we do anything, let's do R or S. What do we have here? OH is 1. Carbon with everything else is 2. Plain carbon 3. H in the back here, this is R. Okay, over here, chlorine is 1. Carbon with OH would be 2. Carbon with just H's would be 3. H in the back here, is that right? So this is also R. All right, both of these are R. Of course, you're not saying, well, since they're bold, they're both R. No, that has nothing to do with it. They have to be bolded. We could have a situation where one's bold and one's dashed and they both be R. No relation. Okay, there we go. Now do the rest real quick. Got them done? Right, that one's R. Yeah? What is this one? S. Bet you a steak dinner that's S. Why? Because the backbone is the same, we just changed the projection. That's going to give you the different configuration around your chiral carbon. All right, you got these others. What is this one? S. 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 R. Backbone's the same. We can just go from there. Or any of the S, R designations the same? No, they're all different. But again, that doesn't give us our final answer yet. Fischer projections. Can you draw a Fischer projection of this compound? We've got 2 chiral carbons. We need 2 crosshairs. We can do that like this. I feel like I want to go over here. I'll be right here. 2, that's 1 Fischer, but the second carbon is here. We're looking at these 2 of the chiral carbons, the 2 crosshairs. Fischer. Crosshairs are your chiral carbons. These are methyls on the end. Sometimes I'll clarify that it's a methyl on the end, yeah. Because for some reason in the Fischer I like to put methyls instead of just leaving a line. And sometimes it'd be like, did you forget to draw something here? Okay. Fischer projection. We did this on Wednesday some. We have to establish what the ground is. This is going to be drawn vertical. The ground, there's the ground. It's down there. This end is closer to the ground. Okay? This is how we typically draw Fischers. We just have instead of 1 chiral carbon, we got 2. They're connected. That's them there. I'm going to get rid of these R and S numbers. Okay. Now we can have the ground here or here. It really doesn't matter, but it's probably easier to have the ground here. If we have the ground there, the 2 chiral carbons, that bond is vertical to the ground. Just like this, to the ground. And since that's the ground, the chlorine is closer to the ground. So we're going to put the chlorine on this carbon so it's closer to the ground. The OH is above the ground compared to the chlorine, so it's going to be on that carbon. So that's how I'm establishing this. Okay. Typically when you draw Fischers like this, your substituents are to the sides. And your carbon backbone, which is 1, 2, 3, 4 carbons, that's straight up and down. 1, 2, 3, 4. Substituents to the side. So the OH is going to be on the side. Basically, we want to look at this. Also, 1 and 4. Methyl here, methyl here. If I'm looking at that Fischer, the methyl's going away from me, correct? That's what Fischer implies. Top and bottom going away. With the methyl going away, with methyl 1 going away, let's look at the next carbon. Is the OH coming to my left or right? With the methyl going away, is the OH on left or right? Well, let's look at it. How do you want to stand for the methyl going away? Stand over here with your feet on the ground and look through there. Pretend I'm 7 feet tall and I'm looking through there. The methyl's going away from me from that carbon. With the methyl going away from me, is the OH on my left or right?
Left.
On my left, because it's coming out towards you. If I'm over here, the OH is on the left. What do I see from here? I see this. What's on this carbon going behind the board that's to my right? I'm drawing hydrogen, correct? And we're drawing the hydrogen in Fischer projections. Okay, that's that chiral carbon. We want to do a model of it. Let's see. The backbone here. Zoop, 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 all the plane. The black is zoop, 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 plane. OH blue coming towards you. Chlorine, coming towards you. Let's switch this. Because look, of course, I can make the chlorine come towards you. Chlorine's coming towards you. But now the backbone is not the same. The backbone, the methyl is no longer the plane. The methyl is now going away. So, okay. Backbone in the plane, forward. That needs to be forward. The only way to get that is to disconnect. And now we have a different configuration. There's the compound on the board. All right. How am I looking at it? I told you I'm standing over here, looking at it. I'm just going to turn it until you see what I see. And I'm just going to do that, looking at it. All right? Now, if I see the methyl going away, which side is the OH on? On the left. There it is. Okay. Now let's look at this other chiral carbon, the lower one. With the methyl going away, what side is the chlorine on? Somebody?
The left.
The methyl going away, the chlorine is on the
Right.
right. Who said left? Why'd you say left?
Because it's coming towards.
Yeah, but which side are you standing on? You don't want to stand over there, because if you're standing over here, the methyl is coming towards you from the carbon. But in the Fischer, what does it mean? It's going away. Basically, with the methyl going away, what side is the chlorine on? We've got to stand over here, feet on the ground, look through here. That's my eyes, okay? With the methyl going away from the carbon, which side is the chlorine on? Well, it's bolded. If I'm over here, chlorine's on the right. Methyl going away, chlorine's on the right. The H is going the other way, it's on the left. There's the compound in the Fischer projection. Okay, we can actually check ourselves, because we know that's R and R. We already did that. Is this R and R? Let's do it again. Oxygen is 1. Carbon with chlorine would be 2. Methyl would be 3. H would be 4. How is the H right now? First off, are we clockwise or counter? Counter, but how's the H? Back or forward? Forward. Things on the side are hugging you, it's forward. Counterclockwise, but the low priority group is forward, so we reverse it to clockwise, and clockwise is R. How about here? Chlorine 1, carbon with O is 2, carbon versus H, this would be 3. Counterclockwise, but the H is coming forward. So we reverse it to R. R, 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 R. We're drawing the same compound. If that's R, R, this should be R, R, correct? Good? There's the Fischer. We'll call this Roman numeral 1. That's the Fischer for Roman numeral 1. Okay, do the other 3 Fischers. Now, actually, you can cheat if you want to from the first one. Okay? And I'm going to go ahead and cheat. And then we'll do another one from scratch a little bit later, because it's the same thing. Boom, boom, boom. What's the difference? Well, the OH is the same, so with the methyl going away, the OH is on the left, correct? There's no difference here. The difference is with here. So with the methyl going away, the chlorine, well, let's do it from scratch. With the methyl going away, which side's the chlorine on? On the left, because you have to be over here. The methyl going away, the chlorine's going behind the board. The methyl going away, chlorine's on the left. Which is different from this. Because this is R, where over here we've got RS, correct? And the Fischer, if you switch places, switch sides, you're going to go to the other configuration. That's Roman numeral 2. But then when I say you can just cheat, I mean methyl, methyl, now we're doing Roman numeral 3. The S is switched, so, I mean the OH is switched, so it's here, correct? The chlorine is just like this, so it should be like this, yeah? And so at this point we're cheating. And then we can do the one over here. It's just like this, so it should be here. The chlorine is bolded, so it should be like the first one, yeah? So it should be like this. Again, we can only do this, well, important to make sure that the backbone is the same. If the backbone went like that instead, you got to look at it differently or consider something else. Backbone's the same here. Okay, we got 4 drawn in Fischers, which can maybe help us. Are all these different? Next thing we can do is, what is the relationship between some of these? First off, are they all 4 stereoisomers? Yes, they're all 4. The name of this compound, you can call this a hydroxy and a chloro. C comes before H. 2-chloro, 3-hydroxybutane. Anybody good with that name? 2-chloro, 3-hydroxybutane. Yeah. They're all that same name. That tells you they're stereoisomers. They have the same name. They have the same connectivity. They all have 4 carbons with a chlorine attached to the second carbon and OH attached to the third. They're all stereoisomers, yes. 2 types of stereoisomers, though. Let's see. Okay, let's look at now compound 1. What's the relationship between compound 1 and compound 3?
Mirror images.
1 and 3.
Mirror images.
Mirror images. Are you looking at the perspective drawing or the Fischer to determine that?
The perspective.
Okay. That's pretty easy to see because we went from both bold to both dashed, and you know that that gives you the mirror image. Yes? You also know that if RR looks in the mirror, what's it going to see? SS. The mirror image of R is S. Right? What about the Fischers? Do the Fischers look like they're mirroring 1 and 3?
Yes.
1 and 3, Fischer's mirroring? Can you see that? Yeah. They are. They're mirror images. Okay, are 1 and 3 different, though? Because everything's got a mirror image. 2 paper clips. I can show them mirroring, yet they're the same thing. Is 1 and 3 the same or different? Who says they're different? Who says they're the same? Okay, we had about a 15% voter turnout. How can you tell if they're the same or different?
Has a chiral carbon.
Somebody, is that you? Who said?
If it has a chiral carbon.
No, that doesn't. If it has one, the answer is yes, but if it has more than one, maybe not. What's the broader thing to say? Or same thing here. How do we know the mirror image of this is the same or different? You can look and see. Basically, I'm asking you: is the mirror image superimposable here? Is the mirror image the same or different? How do you tell? Plane of symmetry. The reason that the mirror image of this is the same thing because this has a plane of symmetry. Where's Waldo? It's right here. Something has a plane of symmetry, and mirror image is going to be the same. Does compound 1 have a plane of symmetry? Don't draw this. Is that a plane of symmetry? No, OH is not mirroring OH. I mean, you got to have two OHs for that to be a plane of symmetry. It's not a plane of symmetry. Is that a plane of symmetry? Don't draw that. No, OH has to be mirroring OH. That's not. Those are the only two places to look. And really, the only place to really look for us is going to be right through here. And no, there's no plane of symmetry. Since there's no plane of symmetry, what does that tell us about the mirror image?
It's not the same.
It's different. It is different. The relationship between these two is what? Those are enantiomers, mirror images that are different. We can put this together. Boom. It's like this. Black here. The green would have to be here. Let's make these mirror. These are the two compounds. They should be, yes. Those are the two, 1 and 3. Are those mirroring?
Yes.
Yes. Same or different? Well, can they superimpose? We've already answered it. Can they? Well, let's put them on top of each other. Blacks. There you go. Blacks are lining up, but the greens are not, and the blues are not. Well, we can make those line up. Yay, now they're lining up. Uh-oh, the blacks aren't lining up. They never will. They never will superimpose. Okay? Mirror images that are different are called enantiomers. Yes. Okay, what's the relationship between 2 and 4? You can look at the perspective. What's the mirror image of RS?
SR.
SR, yes. That tells us it's a mirror image, but that does not tell us it's the same or different. Okay? 2 and 4. I prefer looking in the Fischer. You see how the Fischers are mirroring? Yes. Okay, same or different?
Different.
How do you know they're different?
There's no place.
Is there a plane of symmetry? Is that a plane of symmetry?
No.
No. It does not have a plane of symmetry. I mean, you can go back over here and look. I mean, 2 blacks are mirroring. But is the blue and green mirroring? No, I need to have a green. Well, they will never mirror because they're blue and green. I need to have 2 blues, right? Or 2 greens. 2 and 4 are also enantiomers. Okay. What about 1 and 2? What's their relationship? Is 1 and 2 mirror images? No, the mirror image of 1 is 3. Right? Is 1 and 2 mirror images? No, the mirror image of this would have the OH and Cl here. We need the OH here for it to be a mirror image of 2. The mirror image of 2 is 4. So what's the relationship between 1 and 2? First off, they are stereoisomers. We've already said that. They're all stereoisomers. But they're not mirror images. By default, they're called diastereomers. Okay? 1 and 2 are diastereomers. That's written in your everywhere, your handout, your textbook. Stereoisomers that are not mirror images are diastereomers. What do we know about the physical properties of enantiomers? Identical. Because they have the same sort of configuration, it's just inverted or mirrored. It's the same properties, except for PPA. Diastereomers are really very different, even though they're stereoisomers. I mean, here the backbone is there, the two groups are opposite, where here the two groups are on the same side. At least very different properties. Diastereomers can have very different melting points, like you saw in the bromination lab. One of them was in the 240s, the other was in the 150s or something. Okay, very different. Diastereomers to me is sort of the default category. They're either enantiomers. If they ain't, then they're diastereomers. All right. And of course, if you look at your table, we'll look at that in just a minute. What else can we do here? Back to 1 and 3. 1 and 3 is also can be called a DL pair. Does everybody agree that 1 and 3 is a DL pair? What's a DL pair? Sounds like one's D and one's L. What's that? Enantiomers. 1 and 3, they're enantiomers. One of these will rotate light one way, and one of these will rotate light the other. That's what enantiomers do. And one way is called D, and the other way is called L. So do you agree that 1 and 3 are either one's D and one's L? So we can call it a DL pair. At this point, I don't know which one is D or which one's L, but we can still call it a DL pair. And then these over here. Basically, we have 2 DL pairs on the board. What's the sort of relationship between each DL pair? And we can get at that by saying these diastereomers. Can we give these any name? And we can. If the high priority groups on each carbon are on opposite sides, this is called 3O. High priority groups on opposite sides in the Fischer. What about number 3? Is it also 3O? Yes, high priority groups on opposite sides. Of course, if you think about it more, the mirror image of 3O is 3O. So we can maybe call that the 3O DL pair. And now we have a terminology to sort of get us more specific to what we're talking about. You know. Let's look at the other DL pair, 2 and 4. High priority groups are not on the opposite side of the Fischer. They're on the same side. And this is called what? A rethrow. And of course, the mirror image of a rethrow is a rethrow. How do I remember that? How can you remember that? The high priority groups are on the same side. It's like a capital E. You got your vertical line, and then you got those on the same side. But with 3O, you gotta, when you do a T, you put one line on one side, and you put the other line on the other side to make your T. You gotta be careful. With the EZ terminology, I said E stands for opposite. They're both vowels. That's opposite here. But the E, they're not opposite. They're on the same side. So don't confuse your EZ and your urethra. All right? Did we cover everything here? Yes. There's 4 different stereoisomers on the board. Maximum number possible. All right? Questions as I think and erase. We're going to repeat this with the compound below, which what, has 2 OHs? Ah, okay. I would love to just be able to do this. The problem is you can't do this on your paper, because then you will lose the original, right? So I'm going to kind of start fresh a little bit, but we're going to go through it kind of quickly there. All right. Basically, I'm going to repeat it, except we're going to change every chlorine to OH. All right. Try to get a strategy there for that. We can keep that up there. What do we got here? 2 OHs. OH, what was this first bond here? Folded? We'll keep the same projections. OH, OH, yeah. Boom, boom, boom. What was this one? Folded. You can redraw these or whatever you think's best. And the OH was what? Dash? Okay. Just redraw it. I'm just going to do this here though. Make this OH. Make that OH. You can redraw these. I'm not going to erase and redraw it here. Fischer. I mean, you can also cheat here, right? Because really, you can redo these on your own and just take what you have up there and redo it again and just replace all chlorines with OH. But then let's look at it fresh. There's no need going through this. We've already did it. Of course, I forgot. But if this is going to be the ground and that methyl is going away, the OH is on by left, correct? And methyl going away, the OH would be on the right. Was that the first one again? Except we have OH here instead of chlorine. From there you can cheat. And if we cheated, we would just change that chlorine to OH. And change the chlorine to OH. And change the chlorine to OH. We can still number them as 1, 2, and 3. What's the relationship between 1 and 3? By the way, we can do R and S. I'll bet you a steak dinner that if that's SS, this is RS, and this should be RR. Because the priorities are still the same. We had a chlorine here and it was number 1. With an OH there, now it's number 1. What's the relationship between 1 and 3? RR looks in the mirror, it sees SS. Looks like a mirror image. Same or different? Does one have a plane of symmetry? Don't do this, but is that a plane of symmetry? No, OH is not mirroring OH. And trust the Fischer. That's it. We can zigzag. I got to disconnect. There's no way to get it. Zigzag in the plane, OH forward, OH forward. Okay? Trust of Fischer, do you see a plane of symmetry there? This is the only place to look, really. Think about it. Is that a plane of symmetry? No. OH, we have to have an OH here. Okay. Here's the compound. We can look at plane of symmetry this way. Okay? Forget about the board. Do you see a plane of symmetry? About right through there. Is that a plane? Black marrying black, but blue is not marrying blue. You have to have a blue here. Well, we can put a blue there. Now the blues mirror, but look, now the blacks aren't. Now let's do it again. You're never going to have a plane. All right? What about vertical? Is that a plane of symmetry? No, you got a black over here and a black over here. Now, well, now you need two blacks over here. You're never going to find a plane of symmetry. Trust your Fischer. Since there's no plane of symmetry, what does that tell us about the mirror image? Different. And 1 and 3 is... One and 3 are enantiomers. Yes, that's an enantiomer. Okay, 2 and 4, what's their relationship?
Same.
Basically, okay, other terminology. Is compound 1 chiral? Yeah, that's what we're doing. When the mirror image is different, that means it's chiral. That's what chirality is, right? We'll make sure we know that terminology. Okay, is compound 2 chiral? That is the mirror image different?
No.
2 and 4. They're mirroring. Does everybody agree they're mirroring? 2 and 4? Yeah, same or different. The problem here is you got a plane of symmetry right through there. Do you see how the top is mirroring the bottom? We can put this compound in our hand here. That's forward, this one's back. Black is in the plane, this OH is forward, that OH is back. Let's look at it. Do we see a plane of symmetry? No. Well, what if I put the blue up like that? Oh, look at there. I've got right through here, and I got blue mirroring blue, black going back mirroring black, H going forward mirroring H. That's a plane of symmetry right through there. Everybody see that? Okay. Now, it's not vertical, because I got 2 methyls over here, I have to have 2 methyls over here. But right there is your plane of symmetry. If you wanted to come up here and look at this later, or look, I mean, it's right there. But you can also see it right here. So what's the relationship between 2 and 4? It's the same as this. What's the relationship between this and this? They're mirror images. It's the same. It's 2 of the same thing. 2 and 4 are the same thing. Okay, the answer is the same. Basically, I've just drawn the same compound flipped over. You got to understand that. So how many total compounds on the board here? 3. We've got a DL pair. By the way, is the DL pair a rethrow or 3-0? 3-0. Got a DL pair of enantiomers. And we got what else? We got the other compound. There's one other compound. Is it a rethrow or 3-0? It's a rethrow, but that's not what we call it. Yes, it's a rethrow, but it's a special type. In this case, we call it meso, or a meso compound. What is a meso compound? That's a compound that has chiral carbons. Yes, it has 2 chiral carbons. Yet as a whole, it's not chiral. Because as a whole, well, the mirror image is the same thing. It's because it has a mirror plane. Chiral carbons, yet because it has a mirror plane, the mirror image is the same thing. We call this a meso compound. So how many total on the board? Only 3. 2 of them are just drawn in 2 different ways. So we have less than max. The 2 total is 4, but we have to understand that in this case it's really only 3. It's less than max. Possible for this compound. Questions about this? Questions? Okay, let's see if we can move ahead and maybe do some other examples. We've already defined asymmetric center, stereogenic center. Because an alkene can be a stereogenic center or a stereogenic site, but not all alkenes. Look at this drug here. How many chiral carbons does the following drug contain? Somebody get this? 5? Let's see. Let's see chiral carbon here, 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 here. Any other chiral carbons? How about that one there? No, it's got 2 methyls on it. Chiral carbon is a tetrahedral carbon with 4 different things attached. Did we get them all? 5. How many stereogenic centers does it contain?
7.
Anybody else? Is that alkene stereogenic? Is that alkene stereogenic? Mm-hmm. Yes. Is that alkene stereogenic? Top one. Yeah? Uh-huh. How about this alkene? Is that stereogenic? No, alkenes in a 6-member ring cannot be trans. Okay. Question?
The chiral carbon next to the chiral carbon next to the hydroxyl group in the pentane ring, I thought it wouldn't be considered a chiral carbon because the ends of it, the 2 ends of the ring are the same.
This one?
No, the one near the OH group at the bottom. No, the other one. Yes, this one.
This carbon has an OH and an H. This, are you saying that way is the same as this way?
Yes, I thought the other 2 groups.
It's not. If you come this way, the first carbon is a CH2, but that's not a CH2. That's different.
Okay.
It's not the same root around that ring. It's not. So we got 2 additional stereogenic centers or sites in those 2 alkenes. So 5, now we have 7 for stereogenic centers. How many total stereoisomers possible for this drug? 30? 32? No, it's not 2 to the 5, it's 2 to the 7. N is number of stereogenic sites, that's 7. 2 to the 7 is, what is 2 to the 7? I didn't memorize that one in my math class.
128.
128? I'll trust you. Okay, draw 128 of them. And tell if any of them are going to be meso. First off, do you think any will be meso? I mean, can you imagine any plane symmetry through this compound? I mean, where would you cut through it? I mean, there's only one CF3 group. You're going to have another unless you're cutting right through it. And we ain't cutting right through it because that side ain't mirroring that side. No. None of them are going to have plane symmetry. You're going to have 128. So draw them all and Monday turn that in, okay? Everybody good? No? Okay, let's not do that. There you go. Maybe one of the 128 cures cancer and the other 127 don't do anything. Of the 128, how many DL pairs would you have? Because if you drew the 128, you'll see that 64 of them have a mirror image, and that would be the other 64. And each mirror image would be a DL pair. Yeah? Okay, definition of diastereomers, we did that, yeah. Epimers, what's an epimer? We can look at this by looking at the other handout that you printed and look at Fischer's here, carbohydrates. On biochemistry, you'll look at your carbohydrates and you'll learn them and you'll see them drawn in Fischer projections. Coordination lab due Monday here in class. Okay. All right. Please take a look at this, and we'll look at the definition of epimers there. There's other questions here. Okay. You need to please look ahead, all of this, including the next reaction. And then at some point it refers you to the it says warm-up page or handout. We need to start looking at these. Okay? We need to work our way towards this, and we'll sort of sum everything up by working these problems. Particularly these right through here. That'll be sort of new material or a new approach, or okay. Everything up top though, I think we've covered, except for maybe a little miscellaneous thing. Okay? You need to be pushing ahead with working problems and make sure you have tested yourself and said, okay, do I know this? Do I know that? See some of you in lab this afternoon, guys. Have a good weekend.